Good morning. My name is Mostafa Nouh. I'm an associate professor of mechanical and aerospace engineering at the University of Buffalo. And today I'm going to be presenting on wave mitigation in pseudo-periodic metastructures with a close look at architected pendulums. This work has been carried out at the Sound and Vibrations Lab at the University of Buffalo. So I'm going to jump right in. Everyone here probably knows that architected structures have grown increasingly popular in recent years, mainly due to their ability to exhibit unique and conventional features which are otherwise unattainable. Among these features is the ability to control and mitigate wave propagation through what we famously know as band gap structures. There are two notable types of band gap structures. The first are phononic crystals, which exploit Bragg scattering effects. And there's also elastic metamaterials, which rely on locally resonant structures to initiate such band gaps. Whether it's phononic crystals or elastic metamaterials, the band gaps are essentially regions of forbidden wave propagation within which the structure, even if it's undamped, is going to filter out and reject incident excitations whenever these excitations fall within these frequency ranges. Owing to the periodic nature of these metastructures, the band gaps can usually be predicted from the dispersion diagram, an example of which is in the bottom right corner of the slide, and this is obtained from a single unit cell of the structure. This is a pretty straightforward process. I'm not going to be going into the details of that here. But even though the dispersion diagram predicts the behavior of the chain, of the metastructure chain, it does so for an infinitely long system. However, the band gap effect remains observed and pronounced in the frequency response of a finite structure with well-defined number of cells. Whether phononic crystals or resonant metamaterials, the band gap obviously becomes more and more obvious as the number of cells increase and as we approach the infinite limit which the dispersion diagram predicts. Which brings me to the theme of this talk. A lot of research efforts have recently looked at what happens sort of behind the scenes in the dynamics of these periodic structures, which lead to effects such as band gaps, among others. I present here one of those attempts, which we carried out a couple of years ago, and this looks at some details and patterns that emerge in the mass and the stiffness matrices of a finite periodic spring mass lattice. And these periodic mathematical patterns that you see, also known as the mathematical periodicity of the matrix, are both a function of and a direct consequence of the periodicity of the structure, which we also refer to as the structural periodicity. The dynamic stiffness matrix, K sub D, which is shown here in yellow, is a symmetric tridiagonal matrix, which we can identify as a type 2 Toeplitz matrix. The xi and the eta at the corner elements, which are circled in red, are both functions of the type of boundary conditions, and boundary conditions are a unique feature of finite structures as opposed to infinite systems, which are unbounded. And so the structural periodicity, whether it's the periodic material or the geometric arrangement in the phononic crystal unit cell, maps here to some form of mathematical periodicity in the finite structure. Such identification allows us to analytically develop expressions for the eigenvalues of the periodic structure and gives us several physical insights into the behavior of the finite system, as well as the birth and the evolution of the band gap, but at the finite level rather than at the unit cell level. So for example, once we determine these eigenvalues from the expressions I showed in the previous slide, which are the resonant modes of the finite structure represented by the discrete x's here on this diagram, we are now able to reconstruct the unit cell dispersion diagram using these resonances and for any desired combination of mass ratio mu and stiffness ratio kappa. This also allows us to see beyond the dispersion diagram and identify, just for example, resonant peaks which can emerge within a band gap, which commonly are referred to as truncation resonances, and some other properties which are very unique to finite systems. Some of these features represent the seed and the building block of a lot of the very interesting research that's taking place right now in the area referred to as topological metamaterials. And so this whole structural versus mathematical periodicity analysis, which I briefly showed, begs the question, does structural periodicity always result in a mathematical one? Or in other words, is mathematical periodicity going to be guaranteed for any given periodic structure? The short answer is no, not necessarily, but I'm going to be elaborating over the next few slides. As a case in point, let's take a closer look at an oscillating pendulum, one of the classical problems in mechanics, but instead of a traditional pendulum with a bob, let's consider a uniform pendulum chain. And by that, I mean a series of n discrete masses which are all identical and connected via rigid links of length L. So without boring you with derivations and lots of equations, I want you to take a quick look at the square matrix D, which is an outcome of the linearized equations of motion. And you're going to notice that because of some difference between the elastic and the gravitational potential energies in the derivation of the system of equations between this and a spring mass lattice, the D matrix here does not take the same periodic form that we saw earlier in the type 2 two plates matrix. And so this here becomes an example of a structurally periodic system with an apparent self-repeating cell, as you can see in the schematic diagram, which does not translate to a mathematically periodic system of equations. And so now let's take the uniform pendulum chain and make a small adjustment to it by adding a heavy end payload, M sub t, as you can see on the schematic diagram on the right, which in a way breaks this structural periodicity of the chain. And I'm not adding this adjustment here as a coincidence. We are really inspired and motivated in this research by what we call gantry or overhead cranes. These are used to lift some of the heaviest loads and exhibit some residual vibrations that are usually part of their operation, and they're usually found to be in the low frequency range. An example of that is shown here on the left, and this makes them a very fitting candidate for wave attenuation via band gap mechanisms. And so once we integrate the end payload in the pendulum system of equations, we are now going to get a modified term in the bottom right corner of the constitutive matrix, which can potentially be a game changer in terms of making that matrix periodic once again. So I want you to take a look at the row term, the bottom right term in the M inverse matrix right here. This row term is a function of the mass of the added payload, M sub t. And as that increases, the limit of that fraction is going to approach 1, at which case the matrix perfectly resembles that of a periodic monatomic lattice, or in other words, it's just a chain of identical spring mass cells in series. And we can immediately test this hypothesis by evaluating the transmission or the frequency response of the pendulum system with different payloads and compare that with the response of an identical monatomic lattice. Let's start with rho equal to 100. We already see at that point a close resemblance between the two plots. And as rho jumps to 1000, the two responses almost perfectly coincide, as you can see in the plot. And so in other words, we can think of the lattice as a hypothetical periodic system, which is equivalent to the aperiodic pendulum, just because the governing mathematics of both systems at large values of rho essentially become the same. This interesting feature does not stop here. We can take this a step further by invoking Bragg band gaps that happen in periodic phononic crystals. If we are able to assemble or put together an architected pendulum of some form, which is equivalent to a phononic crystal of a specific configuration. And so this table here shows several iterations from this exercise. Without getting into the details of the table, I would like you right now to take a look at the middle row, which I've highlighted in yellow in this table. This row suggests the following. It suggests that a pendulum chain of alternating masses, M sub 1 and M sub 2, and identical connections, and of course a heavy end payload, is the mathematical equivalent of a phononic crystal which is made of a diatomic spring mass lattice when the following criteria is satisfied. The ratio of the alternating stiffnesses in the spring mass lattice has to match the ratio of the masses of the pendulum chain, and also the spring mass system is going to maintain identical masses of its own. Once that happens, both the actual pendulum chain and the equivalent phononic crystal are going to show the same behavior. Both of them are shown here, and we can now go ahead and again test this claim. If we do that, we'll see once again that the actual and the equivalent systems behave identically. Even more importantly, we now see that this design approach helps us induce reasonably wide phononic band gaps at a low frequency in the pendulum chain, and without a significant size trade-off, essentially because we have a relatively heavy end mass in the engineered pendulum. The band gap that is exhibited by the pendulum chain perfectly matches the band gap of the equivalent phononic crystal. And so we actually decided to go ahead and build this architected pendulum in the Sound and Vibrations lab with the criteria and the design parameters needed to establish this equivalence with the diatomic phononic crystal. We have a complete experimental apparatus to measure the wave profiles and the displacements, and the pendulum we constructed is shown here in the diagram and is mounted at the top to a cart and electrodynamic shaker, which induces excitations at different frequencies of our choice. The white circular elements in the shown close-up image, these are reflective markers, which were attached to the center of the lumped masses to capture the spatial wave profiles under different excitation frequencies. And the way this happens is that a concentrated light beam is shined on the reflective markers, with the surrounding space being dimmed to clearly reflect the oscillations. We track the response of the chain in slow motion via a fixed camera facing the setup. I'm going to now sit back and have you watch the experimental result. Before I do so, I want to point out that in order to determine how heavy the end payload needed to be in our experimental setup, we swept through a range of rho values. And as you can see here, as the order of magnitude of rho increases, the resonances on the vertical axis split apart and open up a band gap as we expect, which at the limit of rho equal to infinity is going to approach the Bragg band gap of the chosen equivalent phononic crystal. We end up going with rho equal to 16.6, which gives us a sizable band gap that we should be able to capture and observe in the experiment. So as you can see from both the numerical and the experimental frequency response data that's shown here on the right-hand side, we anticipated and got a band gap which spans the range 14.7 to 26.5 hertz. On the left, you can see snapshots from the recording I just showed you, which correspond to 3.3 hertz, 9.6 hertz, and 16 hertz, respectively. The latter, of course, the rightmost column, falls within the band gap range and confirms the experimentally captured band gap. And you can see then the wave profile that's shown here in yellow. I do invite you to watch an entire video recording of this experiment in real time and slow motion on our YouTube channel. And for the full mathematical framework and the detailed derivations of the motion dynamics of the pendulum, please check out our paper on this project and/or reach out to me directly, and I'll be happy to share more information offline. And so with that, and for the sake of time, I'm going to conclude. I quickly want to express my thanks and gratitude to the SES virtual conference organizers for all the effort that they put in towards making this event successful. I would also like to thank my former and current PhD students, Hassan and Jesse, and my sponsors who made this work possible, and thank you all very much. I'm now happy to take any questions.